past, present, and emerging. Today, we'll be hearing from the ARC Centre of Excellence for Climate Extremes, or CLEX. Today, our speaker is Dietmar Dommermuth, who works in the School of Earth, Atmosphere and Environment at Monash University as an associate professor. Now, Dietmar, originally from Germany, is an advocate for understanding climate change, and his research passions cover climate modelling, El Niño, and deconstructing high-dimensional climate systems into simplified models. So Dietmar is actually a physicist by training. So all of the AIP members who are joining us today, Dietmar is traditionally a physicist, and he completed his Masters in Science project in high energy astronomy using an observatory on the Spanish Canary Islands. So Dietmar is also responsible for creating and developing the Monash Simple Climate Model. This is a public webpage for educating about climate models and climate change with the use of a simple interactive climate model. It's really very detailed, and I encourage you all to check it out after the talk to see how varying things like cloud cover and CO2 in the atmosphere can significantly alter the climate. And I'll put a link to the Monash Simple Climate Model webpage in the chat for everybody a little bit later in the talk. So just a couple of housekeeping issues. The current talk will be recorded. And we do encourage you throughout the talk to post questions in the Q&A box. So you can ask these at any time through the talk, and we'll collate them and ask them of Dietmar as we get towards the end of the talk. So with that, I'd like to pass over to you, Dietmar. So thank you very much for joining us, and I look forward to hearing your talk.
All right, thank you for the introduction. Hello, everyone. It's me, Dietmar Dommermuth, and I will now start share my screen. And to start the PowerPoint. Okay, here we are. Should get started, hopefully. All right, so the topic today is climate modeling. And initially I thought the audience would be mostly people from the Physics Center of Excellence. But I can now notice that a lot of the participants are actually from the Atmospheric Science group. So you might be a bit disappointed if you're from the Atmospheric Science group, because I'm aiming at physicists who are not in the climate community. But it might nevertheless be a good background for you. I mean, even though I'm in the Center of Excellence for Climate Extremes, I will not particularly talk about climate extremes research, but I will more talk about the general background of how do you model the climate. Okay, so here's the overview. What I would basically do is I will show you two approaches how you simulate the climate. The first approach is what we call energy balance. So the idea is that you follow the energy flow, and if you follow the energy flow, you understand what the surface temperature would be. This is an approach that is used in education and in simplified models, and it helps you to get an idea of how the climate system works. This is, however, not the approach that you use when you really want to know the climate systems in detail, or you want to make projections into the future. This is the second approach, which is called the general circulation model, which is kind of the state of the art. So this is what everybody uses who wants to know the best simulations and best projections into the future. Then they use a so-called general circulation model. And that idea is basically you follow the flow. So you have the atmosphere and the ocean that is constantly moving, and you're trying to follow the flow and try to understand how things are moving around. This is why this approach is called general circulation. Maybe I have to get myself a pointer here. Okay, here's my pointer. Okay, and after that, so this is a little bit of an introduction, and a little giving you a bit of overview. I'll show you a little bit about the current issues, and just give you one highlight on current issues about what we are currently concerned about or what we are thinking of. And then at the end is a Q&A section, which maybe for those who are interested in and haven't much context into climate, we might do a little bit more of questions beyond this talk. All right, going to the first one. So energy balance. So the idea is, here's a little sketch. You have the surface of the Earth, and you want to know what the surface temperature is. And the basic starting point is what we call energy balance. So you have energy coming in from the sun, energy coming out, which is black body radiation. So every body that has a temperature loses energy. And then in the atmosphere or in the ocean, energy can come in horizontally by transport from energy into the system and energy out of the system, or actually energy can also go into the subsurface, in particular of ocean points. Then the subsurface ocean can actually store a lot of heat. And looking at this balance is a good way of trying to understand the climate system. And this is what we will do first. Okay, and what I'm trying to do now is I try to build this up step by step. And this has been described in a paper a few years ago that I did together with a student, Janine Flöter. And it's called the globally resolved energy balance model. It basically takes this idea that is typically in textbooks in climate, and I put it a little bit on another level that you can actually do this for every point on the Earth's planet. So it's an example of how you can do this. And it's illustrating a little bit of how we think about modeling the climate system. So I will build this up slowly. So here we have an energy balance equation. So the left-hand side is the change in temperature. So dT surf dt, that's the change in temperature over time. So what we call the tendency. And then here is the heat capacity of the surface. And then we want to know how is this changing over time. So we need to figure out the right-hand side. What is driving this? What makes it warmer? What makes it colder? And here I have a little sketch. So the Earth has some areas where it's ocean, where the heat capacity would be of the upper ocean, typically 50 meters of the ocean. And then we have land points or ice points where the heat capacity is typically that of a 2-meter layer solid soil or ice, which is similar heat capacities. Okay, let's go through this step by step, and then you will see what kind of processes are important in the climate system in a simple situation. So in our first approach, first of all, the obvious one, it's sunlight coming in. Then sunlight is reflected at clouds. So you need to know the cloud cover. In this simple case, we just assume that clouds are a boundary condition. And then you need to know what is the surface color. And ice-covered regions will be bright, and bare soil, earth, or forests will be dark. Oceans are dark. So you figure out the sunlight that you're absorbing. So you can have a little equation for this. And there's many little these equations, but I will not show all of them. I'll just show you one example. So the sunlight basically is the solar constant here, the S naught. And then the fraction that actually at a certain latitude and time of the year will actually hit the surface. And then a part of it is reflected at clouds, and a part of it is reflected at the surface. And if you know the clouds, then you know how much it's reflected in a simple way. And at the surface, you might actually make the surface color depending on the temperature. Meaning when it's cold, the surface is bright because it's ice covered. And when it's warm, the surface is dark because it's not ice covered. That's just one example how you can simply simulate that. And the next one would be the thermal radiation. So everybody has every object has a black body radiation. So the surface loses heat. That heat can go right into space, but a part of it actually will be absorbed or by the atmosphere, in particular by clouds, and also by the greenhouse gases in the atmosphere. And then the atmosphere itself will start to radiate thermal radiation, and therefore part of it will come back to the surface and also from the clouds. So if you want to know thermal radiation, how much you're losing energy by thermal radiation, you need to also consider about how much you are gaining from the atmosphere. So you need an atmospheric tendency equation as well. So that's, we see things now starting to become a bit more complicated. And then you have a thermal radiation from the atmosphere. So we would also need to have a tendency equation or energy balance equation for the atmosphere. And in this simple situation, we just assume the atmosphere has one temperature at every given point on the Earth. Then the most important greenhouse gas, or the most important gas in the atmosphere that makes the atmosphere actually radiate thermal radiation is water vapor. And water vapor has a lifetime in the atmosphere of about 10 days. That is that it evaporates from the surface, the water evaporates from the surface, turns into water vapor, and then it rains out, and then it's gone out of the atmosphere. So we need to have a tendency equation for these water vapor in the atmosphere as well, to understand how much thermal radiation is coming from the atmosphere. So we already get another equation that we need to also look at the tendencies. In this case, it's a mass tendency. So we think about how much moisture is in the atmosphere. It's not an energy balance, but it's a mass balance. Okay, that gets us to the next thing that we need to simulate. We need to simulate how water gets into the atmosphere and out of the atmosphere. So it gets into the atmosphere by evaporation, and it gets out of the atmosphere by precipitation. And that is these two terms here. And then evaporation is a phase transition of water that involves latent cooling. And condensation, so rainfall, is a phase transition from gas into liquid that involves heating. So we have latent heating happening in the atmosphere. So the water heats the atmosphere when it condensates to raindrops or to clouds. And it actually, at the surface, it cools when it's evaporating. Okay, and that next thing is then that water can be transported around in the atmosphere, and also heat can be transported around in the atmosphere. So we need to know how the atmosphere transports things around. And we do this in a simplified way. We have one term here, which is isotropic diffusion. So we just assume that the atmosphere has a diffusivity. And then we have a second term, which is advection. So we are assuming a mean flow in the atmosphere. And in this case, again, this model is assuming a background mean flow. It doesn't try to estimate it. And then we advect things with the mean flow, both in terms of moisture here, and then the upper one in terms of heat. And then the next step is that in addition to the radiation balance between the atmosphere and the surface, there can also be a direct contact between the atmosphere and the surface. It's what we call sensible heat flux. And therefore also heat can be exchanged. And that also is important when you go between the surface and the ocean. So the ocean is fairly deep, it's 4,000 meters deep, but the interaction between radiation and the sensible heat flux with the atmosphere is typically only in the upper 50 meters of the ocean. But the upper 50 meters of the ocean can interact with the deeper ocean on longer time scales than a year and 10 years, 100 years, and 1,000 years. So therefore, you need to consider how much heat you are actually losing into the ocean. So it's a sensible heat flux into the subsurface of the ocean. And final element that you want to consider is sea ice. Sea ice has not only the effect that it changes the color of the ocean. So usually the ocean is fairly dark, but if it's sea ice covered, then it's fairly bright. But the more important effect of sea ice is actually that the sea ice insulates the ocean. So there's no more thermal contact between the cold atmosphere in winter and the ocean, which is above freezing when it's liquid. So that actually has a big important insulation effect, and that has also been simulated. So these are basically the main things that you have to consider to understand the very rough structure of the climate system. It's basically a zero order guess, what you have to consider if you just want to know what temperatures you have at different places, or how much precipitation you might have at different places. Now, this is, of course, a very crude way of doing things. And you will notice when you do this that your model will either blow up or be very unrealistic. Unrealistic in the sense that it's 20, in polar regions, it might be 20 degrees off. And in tropical regions, the model might be 5 degrees off. And sometimes these differences matter. And if you want to know it more precisely, you can put in what we call correction terms. This is called, in our field, sometimes called flux corrections. And these are used to maintain your model at the reference state that is observed, because many processes in the climate system are state dependent. So if you are at a certain reference climate, you will have a different way of responding to external forcing than when you have a different climate. The easiest way to understand this is if you have snow cover. So if your normal climate would have snow cover in winter, but your climate model is 10 degrees too warm and doesn't have snow cover in winter, then obviously it will respond differently to any kind of changes. So therefore, you often introduce correcting terms into climate models. And there's different ways of doing this. In this case, these are so-called fluxes that you artificially correct your balances, that they on average have about the correct balance as they are observed. Okay, that was basically a simple way of a model. So we see that at the end, we have basically 4 diagnostic equations here, 4 prognostic equations, so tendency equations. And in the background, there are a number of other equations to figure out the individual terms that are on the right-hand side of these equations. But it's still a fairly simple model compared to the complexities that the other models later on will have. And this model is then calculated on these equations are then calculated on a 3.75 degree grid that looks roughly like this. You can see that it's not resolving everything that you might care about. So there's almost, there's no Tasmania, no New Zealand. Sorry for you folks. And there's also no United Kingdom or no Italy. So it's a coarse resolution model. These are the kind of resolution that models used to have in the 1990s. And it's a good way of illustrating things. You can, of course, calculate these equations on higher resolutions, but you don't gain more information. So that's why I did not resolve this on a higher resolution, because not more information is gained by that in this simple setup. And the time step of such a model would then be 12 hours, but not resolving the daily cycle. So it's really a climate model focusing on the monthly and longer time scales. Okay, I'll show you some examples. And this is based on this web page, which we call the monosimple climate model. And I'll show you some illustrations of how this is nice to illustrate how the climate system works. So we go to the web page, and let me go here to full screen. So I hope you can see that. Okay. Okay, this is here. This is not where I wanted to go. I wanted to go to the next one. Okay, so this is an example of what you can do. So you're running the simulation, and you have, in this case here, you have two experiments, one on the left-hand side, and you can switch on and off these processes that I just illustrated. So ice, clouds, ocean, atmosphere, CO2, and the hydrological cycle, so precipitation and evaporation and water in the atmosphere. And on the right-hand side, you have another experiment where you can also switch on and off things. And in this case here, I switched off everything, and then the Earth is basically like the moon. And if you just focus on the seasonal cycle here that is measured here, so you see every time the map switches, it's a different month. So it goes through the calendar years and shows you the climatology as it appears over the year. If you focus on Australia, you can notice that in winter, then without an atmosphere, we would be have minus 50 degrees in winter. And then in summer, it would be about similar temperatures, about 20 degrees. So if you would have, in general, without a climate system, you would have fairly extreme seasons and a different overall mean temperature. And just to illustrate a few things here, so let's say we turn everything on and just checking. So now they are both the same. And let's say we do a simple experiment, we take away the clouds. And then obviously if there's no clouds, more sunlight is absorbed, and you would guess it would get warmer. And this is actually what's happening. You can see without the clouds, the Earth would be much warmer. And here in the lower figure, you see the difference. So the cooling effect of the clouds overall is about 20 degrees, which may seem a lot, but that's actually there, because about 30% of the sunlight is reflected by the clouds, a little bit less than 30%. Another interesting example is if you do the oceans, if you take away the oceans, and the oceans do not necessarily have an overall warming or cooling effect, but if you look at the seasons and look at Australia, you would see without the oceans, the seasonal cycle in Australia would be much more extreme. You would have more than 40 degrees in summer, that is day and night average, and you would have below 20 degrees in winter and day and night average. So the ocean's main effect is that they moderate the seasons, and they do this because of the large heat capacity. They slow down the warming and the heating in summer, so that in spring things doesn't heat up as fast, and in fall things doesn't cool down as fast. Obviously today more interesting is the CO2 effect. If you take away the CO2 from the atmosphere, you see the Earth gets obviously much colder, about 10 degrees colder in this model. It's a simplified model, so don't take this number too seriously. But the interesting aspect, if I stop this here now, you can see the CO2 level in every point on the Earth is the same, but the response on the surface temperature is not the same everywhere. You can see in this model here, that would be in this situation, if you take away the CO2, there would be very strong response here over North America, but almost no response here at the sea ice boundary in the North Atlantic. On the other hand, around Antarctica, then there would be a very strong response. And that is kind of maybe counterintuitive, because you think initially CO2 is everywhere the same. Why is there different responses at different points? That is because all the elements in the climate systems are interacting. To illustrate this, you can turn off all the other elements. So let me take away the hydrological cycle, the oceans, the clouds, and the ice. And I do this on both sides. So now the difference is only that they have an atmosphere on the left with CO2, and the atmosphere on the right has no CO2. And let me update the figure. And now you can see they are very similar, but there's only an offset in temperature. So the temperature offset is almost everywhere the same. So without interactions, actually the CO2 effect is really simple, but with all the interactions in the climate system, the CO2 effect is more complicated. And this is actually the reasons why climate scientists over the last 50 years have spent all their time in trying to make the climate model more and more complicated and more precise, because there's all these interactions in the climate systems that make things more complicated. How do I get back in this mode here? I don't know. Okay, let me move on to the next one here. You can also do little scenarios, what we call scenarios. That is, you change the boundary conditions, like you increase the CO2 over time, like in this one here. So here we have the CO2 increasing over time as what is considered business as usual, so nobody cares about climate change. And then you see how the temperature changes over time. So if you go back here, 1970s, and then until today, 2020, you see we have a little bit of warming. In Australia, about 1 degree, a little bit more than 1 degree. You see here also the summer and the winter, and you see it's slightly different in summer and winter. But you can also see so far not much warming has happened, even though it's already substantial, but it's not compared to what's going to happen in the next 100 years, you can see that it will be much more warming eventually. You can also notice that there's a pattern in the warming, that it warms more over land than over the oceans. And actually it warms more in the winter time in the polar regions than it warms in the summertime in the polar regions. But you can also do some kind of fancy scenarios, not just interested in climate change. You can also ask, like, if you're interested in astrophysics or more like extra tropic, other planets or so. Here's an example where you actually, I'll stop it. So we're changing the distance of the Earth to the sun. So this is illustrated here in this sketch. So our model is currently between Earth and Venus. And then I can move it towards Earth. So that's our today's climate. I have to stop it, wait a second. So this is today's climate. And then if you move it more towards Mars, it will cool down because you are further away from the sun. And you can see it cools down pretty fast. So within, let's say 5% more further away from the current radius, the Earth will basically freeze over. And if you go 5% closer, the Earth will already start to be getting really hot. Average temperature would be like in the Sahara in summer. And then if you get closer to the Venus, it gets really hot. And another nice example is you can tilt the Earth's axis. So you can see here the Earth's axis, I have to stop that. It's usually like this. So like this, 23 degrees. So that is normal. And then you can tilt the axis and see what would happen. And obviously, if you tilt it to an extreme point, let's say the North Pole would face the sun in one half of the year, and then the other half of the year would be away from the sun. That would actually turn the tropics into the colder region, and the polar regions would be the warmer regions. Okay, so these are a few examples with this model. Let me get out of this here. I think these were all the examples I wanted to show. Okay, so this is what you can do with a simple model to get an understanding of how the climate system works a little bit. Okay, let me get to the next point. So this was the simple idea and how things work. Wait a second. I have to look at the time. So let's go to the more complicated and the top end approach, which is the general circulation model approach, or what state-of-the-art climate models are doing, or the ones that you hear about future climate change projection, like from the United Nations IPCC report. These are these kind of models that are called general circulation models. So basically, the starting point for general circulation models is that you basically run a weather forecasting model, but instead of running it for a few days or a week, you running it for a few hundred years. And therefore, you need to somewhat change your weather forecasting model to be slightly different. But you can think of today's climate model being basically a weather forecasting model on running it for a very long time. And maybe then the first equation that you would write down for if you're interested in weather forecasting, you are really interested in how does the air move around in the atmosphere, or how does pressure systems like low pressure and high pressure systems move around. So a starting point quite often is a so-called momentum equation. So on the left-hand side, you would have the momentum, so how things are moving around and how is this changing, so the tendencies and the momentum. And then on the right-hand side, you would have the Coriolis forcing, the forcings that actually drives the changes in the momentum, like Coriolis forcing, pressure gradient, gravity, and friction. And then there's many, many other things following. I don't go through all of this, but I will show you a few more things just in terms of the sketch later on. So there's many, many processes involved in a general circulation model. And rather than showing you all these equations, I'll show you a few videos to illustrate what these things look like. So let me go back to my, now I don't see this. Okay, do you see any Chrome browser? No, I don't see my Chrome browser. Okay, I have to stop this here. That's not it. I lost my, that's also not it. Oh, my window has disappeared. Okay, I have to start this again. Okay, might take one more second. Okay, So this is an animation, which you can hopefully see now, of today's circulation and the surface winds of the atmosphere. And down here is Australia. We can zoom into Australia a little bit. And you see a little bit of the complexity of the flow. And this is so this is observations basically put into an atmosphere model and then put together that you can see what the current situation looks like. But it's based on observations. So this snapshot is not necessarily a climate model simulation, but it uses a climate model just to visualize and put all the observations together. And you can see a little bit of the complexity of the flow. So you see a little low pressure system here to the right of Australia. I think you can see a tropical cyclone here near the Philippines and Taiwan. You can zoom in a little bit. And you can see the flow a little bit around Antarctica. You see a little bit of the structure of the flow. To wait until it builds up. So you see all these little wave-like structures and eddies and low pressure systems or cyclones following around Antarctica. So this is kind of what we are aiming and simulating. So let me see how I get out of this. Okay, now I'll show you another animation. I uploaded this all before, but now I have to skip one. Okay. Okay, this is the so this is now a simulation. Again, this uses observations, but this time in the ocean. And this project is a NASA project called ECHO, and it tries to get all the information from ocean observations into an ocean model, and then tries to estimate the state of the ocean. And what you see here in lines is the streamlines of these ocean currents. And when you follow the animation, you will see a lot of structure in the ocean. It looks like there's little rivers going through the oceans. The one that you currently see here is to the lower left is the Gulf Stream, and then the Gulf Stream extension crossing the Atlantic. And you see all these little eddies in the ocean. That illustrates how complex the ocean is. So I go through this animation, and the animation will go basically across the Earth, and at some point it will be in Australia. So you see mean flows, but you also see lots of little eddies, like the one here in the Gulf of Mexico. Then you see other eddies here. You see very small structures. Then on the equator, you will see very high-speed surface circulations that very suddenly change because they are pushed by winds. Then you see here this little dance of lots of little rings. So we have these from the Indian Ocean. We have relatively warm water coming here along the coastline in the so-called Angular current. And then this splits into little rings, little eddies, and they slowly cross the Atlantic on the time scales of several months and years. They slowly propagate. So these eddies will stay around for a while, and they will be fairly warm eddies in surrounding cold Atlantic water. Move this on. So you see that's a fairly complex structure that these ocean models need to simulate in order to simulate the climate system. And there's all kind of very intense currents, typically along coastlines, and also intense currents on the equator. And I think at some point we move to Australia. Here's Australia. So you see here to the east of Australia, we have also eddies that typically go from here and then be somewhere in the Tasman Sea. And you have coastal currents. And then you have the Pacific again with the intense current, which suddenly changes because they are sensitive to the surface winds. Okay, let me stop this here. Okay, I have another one that I want to show you. Stop this one. Okay. So that's the last animation I want to show you. So this is a simulation of of 1 year, and it actually simulates from a starting point CO2 concentration in the atmosphere. And what you see, the fluctuations in the CO2 is mostly natural CO2. And you see quite often there are blooms, especially in spring, from the northern hemisphere coming from all the agriculture fields. And the red one is more intense CO2, and then the yellow greenish ones is lower CO2. But it's the natural cycle of CO2 that you see here over the year. So now we are in spring, you see it now red gets intensified, because that is what the agriculture does mostly. And then you will see during the summer, maybe I skip forward a little bit. So here, this is now early in summer, so late in spring. And you see how all these little eddies in the atmosphere move around the CO2 and mix it. And there's more in the summer, in the northern hemispheric spring on the northern hemisphere. And now you see during summer, this all gets away, because during the bloom in summer, the trees and agriculture pick up all the CO2 from the atmosphere and take it up. And then in the next winter and spring, this comes back into the atmosphere. What you can also see here is a different color bar, is this white and gray scale, which is carbon monoxide, which has to do with wildfires. And you can see some of these wildfires in the southern hemisphere and also over Australia. So again, this is also a model simulation. And you can see there's very fine structures and a strong interaction between the surface and what's going on at the surface and what's going on in the atmosphere. Okay, that's this one. Let me go back to my slides. Okay, so the last one is something from our CLEX Center of Excellence, and that is trying to get to the very highest resolution that we can run our current climate model, which is more like weather forecasting. So it doesn't run for a long time. It actually just simulates 2 days, and it simulates 2 days in 2017, when the tropical cyclone Debbie hit Queensland. And I'm just starting it, and I run it several times. You can see what happens. It's just 2 days, 2.5 days. And you can see sometimes late in the days, somewhere over the Northern Territory, there will be strong clouds picking up, like here right now. You see that's these little convection clouds picking up. I run it again. But when you look at this, it looks like the real world, right? I mean, it looks like an anime, whether you would watch it from satellite and you would see the real world. But what you are seeing here is not the real world, it's a model simulation. But the amount of realism in this simulation is amazing, because you see all these little details that you see in the real world, these little fronts and very detailed lines and little clouds picking up. So just going back to the technical details. So this is a simulation where we put Australia into a little grid of 400 meters grid points. So that's about 12 billion grid points. It runs on the NCI computer in Canberra. It takes about a week to run this model. And it's 2 million CPU hours, if that means anything to you. But you get an idea of how complex it is if you're running your own simulations. And it's the biggest simulation that has been done with the Australian model so far. But you can see it's a focus model only for Australia. It's not a global model. Okay. So that was a bit of giving you an idea of how the climate system looks like in high resolution or state or high-end description of the climate system. And this is what climate models are aiming for. But it's a little bit on the over top end, I would say. I mean, the kind of models that most climate scientists work with are not as complex as these ones, but they are somewhat trying to aim for this kind of complexity. To give you a little bit of an overview how this evolved over time in the last about 50 years. So climate models that want to make projections into the future, how the climate system would respond to CO2, they basically started out with an atmosphere model that's, my mouse here, my pointer. So it started out basically simulating the circulation and radiation. And then someone in the 1980s, they tried to simulate the clouds, the precipitation, and the land interaction. And you will see over time now it becomes more and more complicated. So obviously, to simulate the climate, you need to simulate the ocean circulation as well. So you need to see how heat gets into the ocean and how the ocean is circulating and how it's interacting with the deep ocean. And that also evolves, then you have to simulate sea ice. Sea ice is not only just melting and freezing, it's transported around in the ocean. So that all of this will interact with the atmosphere. And then it becomes more and more, so these are basically the physical things, is the core, what makes the climate predict temperatures and rainfall. But then there's other things getting involved that become then more complicated. For example, are aerosols, so dust particles or chemical particles in the atmosphere. They influence this formation of clouds and rainfall, and they also absorb radiation. So they're interacting in the climate system, and they are also something that humans or the anthropogenic industry is producing. So it is important to understand how aerosols are affecting the climate system. Then there's a carbon cycle. So CO2 is not in the atmosphere forever, but it actually exchanges between the land, the ocean, and the atmosphere. And these exchanges you need to simulate if you want to understand how the climate system evolves on longer time scales, so more than 100 years or many decades. And that it involves chemical elements, biological elements, and physical elements to understand the carbon cycle. And then you're getting into the atmospheric chemistry. So in the higher levels of the atmosphere and the stratosphere, ozone is a very important greenhouse gas, but it's also chemically very active. So if you want to understand these chemistries of the atmosphere, you need to simulate the chemistry in the atmosphere. And also at the surface, vegetation is changing according to the climate system. So if it's colder or wetter or warmer or drier, the vegetation will adjust. And that means the surface will adjust, and that changes the way that the surface over land interacts with radiation or heat or moisture. So evaporation and precipitation is affected by vegetation, but also the pickup of carbon and other chemical interactions are happening with the vegetation. So it's an important element in detail. And then land ice, like ice sheets over Greenland and Antarctica, they can influence water balance, but also the sea level. And that has an effect onto the climate system as well, which is now more or less the present day. So you see the present day climate systems are actually highly complicated. And there's all kind of interactions. So every line here I draw is some kind of interactions between systems. And you can think also of every little circle here being a different climate community group. So people who work on the land, they work only in the land cycle more or less, but they have not necessarily much to do with the carbon cycle of the cloud people. And so it's an interdisciplinary team working on a climate model. Just to give you an idea, so the simple approach that I showed you at the beginning is basically 700 lines of computer code, runs on a laptop, and takes about, for a simulation, a minute. And then the current state of the art, what most people in our community use, is typically 4 million lines of code, runs on a supercomputer in Canberra, and it takes about 2 weeks for the same kind of simulation. So that's kind of the CPU benchmark that we had. Okay, last point that I wanted to show you is current issues. So there's obviously the complexity is huge in climate systems, and there's millions of issues that people are working on. And it's kind of ridiculous to say what are the current issues in climate science. But I pick out one, basically, which I think is the overarching issue in the climate community. And this is trying to predict what will happen to our climate system if the CO2 is doubling, which seems like a no-brainer, because obviously when CO2 is increasing, it should get warmer, but in detail, it's actually more complicated. So climate models are great, and I showed you a lot of great videos based on climate models, but they are not perfect, right? In some aspects, actually, we wish that we could improve them, and we would hope for improvements, but these improvements turn out to be really, really slow in some aspects. And these aspects involve, unfortunately, the question is how much does the climate system respond to CO2? So this is what we call the uncertainty in climate sensitivity. So climate sensitivity means how much does the global mean surface temperature change per doubling of the CO2 concentration. So if the climate sensitivity is 3 degrees, that means global mean temperature changes by 3 degrees if we double the amount of CO2. And here's a graph fairly in a new publication that looks at this, how this uncertainty over this climate sensitivity has changed over time. And kind of the first study that reported this was in 1979, the Charney report. And it says the climate will change by about 3 degrees with an uncertainty of plus minus 1.5 degree. And then you look over time how many more studies came out using climate models and trying to predict this. And then it became also into a bit more detail because there's actually different estimates of how you estimate the response to climate. There's the so-called equilibrium climate sensitivity. So what would be, if you wait long enough for the climate system to adjust to the change, what would be the response? This is kind of theoretical because it would take many 100 years to figure this out. But therefore, often people look at the transient response. So what is happening over the 21st century, and what is the climate at the time when you have reached double CO2, which is this TCR, the transient climate response. And you can see this transient climate response typically a little bit lower than the equilibrium ones, because obviously the equilibrium ones will take a little while longer and then they warm up a little bit more. What we can notice is the very latest estimate of the uncertainties and the mean response is larger uncertainty than we had about 50 years ago or 40 years ago. So you might say there's absolutely no improvement in the uncertainties of our models over 40 years of time, if you want to be putting it in a negative way. Right? It looks like we have not achieved to make any kind of improvements in the models. And the reason for that is not necessarily we haven't improved the models, it's because the models became more and more complex and more things are now interacting. While in the 1970s, they only had the atmosphere and a simplified ocean. But nowadays we have chemistry, biology, and the carbon cycle, and all of these things are interacting. But unfortunately, it is the way it is that the uncertainty in our estimates from models is still very uncertain. So we know it's about 3 degrees and then plus minus a range, which we couldn't make any narrower over the 40 years of climate modeling research. So it's very likely that we will reach doubling of CO2 by about 2070, unfortunately. And it looks like we will not be able to narrow down the uncertainty just based on models. So our improvement from estimating double CO2 will unfortunately come from the fact that we will simply observe it instead of modeling it, which is very unfortunate. To illustrate you these uncertainties, I show you here an example, which is from 2007 climate models. So these are the average of 24 models trying to predict the warming pattern. And you see that that's more warming over land and less over the oceans. And here's 4 of these 24 models. And you can see they disagree quite a bit. For example, this US model here from NASA has a cooling point in the North Atlantic, where the Chinese model has the largest amount of warming. And you might wonder, how can this be, right? If you look at this model, in each of these models, they are actually certain that this is correct, but they are not varying much. This is actually always the case in these models. If you run them, they will end up with these kind of responses, but these responses are inconsistent to each other. Similar is this in rainfall. So in rainfall simulations, you have a fairly complicated rainfall response pattern. That is here, the blue regions have more rainfall in the future, and then the yellow and orange regions have less rainfall in the future. And then the hashed area hashing here, areas indicate that the models don't agree. And it looks like here over Australia, there's no agreement or no signal. So nothing is changing over Australia. I show you a set of models. This is all again from 2007, and it's 36 different models trying to predict the future changes in Australian rainfall. And you can pick your model. And for example, you pick this one here on the lower left. It says it will rain more in the future by about 10% per degree global warming, so about 30% more rainfall in the future. Then you pick one of the Australian models, the CSIO model, a lower resolution version of the CSIO model. Yes, the other 2 ones here are also CSIO models, Australian models. But this one here would then predict less rainfall into the future and about 30% decrease. And actually these models by themselves think that this is what's happening. But you see that the models are contradicting each other. And that is currently one of the main issues in our climate community. So how do we get to this issue? So I think it's the sheer complexity of these models that gets us into this issue, that we have all these systems interacting. It is also that climate models are developed by little research groups. There's no very large groups working on this. These are all little groups, quite often PhD projects that build little elements in these systems. And the sheer complexity of these models is overwhelming. And our models are still considered coarse resolution. Just to illustrate here, so I showed you this animation of the ocean with all these little eddies and circulations. But if you look at the current resolutions of ocean models, they look like this here, which is just here shows temperature. But you can see this little boxes show you the resolution of these models is still fairly coarse to what you actually need to simulate in the ocean to make it realistic. So many people in our community suggest the following: we need a global project on the size of the Apollo moon landing to actually create models that are orders of magnitudes more complicated and have computers that are 10 times or 100 times bigger than the ones that we have in Australia. So that is one suggestion, that we need to massively increase our effort to make this more accurate. That basically means we create models that are resolving thunderstorms all over the Earth and simulate them for many hundred years, and the same with ocean eddies. Another idea that is in the community is that we use artificial intelligence optimization of these models. But if you know something about optimization, typically it requires a lot of large database and many iterations, thousands of iterations. To run the model once, to get an idea of what the climate systems look like, you have to consider that you need 1,000 CPUs running for a week to have one realization of your model. So if you do think about artificial intelligence optimization of climate models is interesting, but it requires a massive amount of computing time. So both of these approaches would mean that we need to massively increase the scale of which we work on climate models. Okay, coming to the end. I don't have any summary. I just gave you a little bit of a snapshots, but you might have questions. And if you are not in the field, you might have heard a lot of things about climate change that I haven't talked about here at all. But feel free to ask any kind of questions you want to ask a climate expert or so. I might know a little bit about it, but maybe I can give you some idea. All right, thank you all for joining, and maybe opening up for questions.
Thank you very much, Dietmar. What a terrific talk. Gee, it gets complicated, doesn't it? So yeah. The Q&A box is open if anybody has some questions that they would like to direct towards Dietmar. I might start off if you don't mind. I can see that the models are getting more and more complex, and you're right, having a global effort to start looking at it might be important. Can you tell me how important it is to test your models on known historical data? How that helps you improve your models?
This is absolutely essential. So every model development basically starts with the observations. I mean, there's many processes that don't have natural physical laws, like, for example, the formation of clouds and precipitations. They are so complex that we need to take observations and try to mimic observations in some kind of statistical sense, or what we call parameterizations. So model development usually starts with observations and trying to formulate equations based on the observations that we see. So there's no model development without observations, really. So this is really core to any kind of model development. And of course, we trying to verify our simulations based on observations. But there are some things that we do not really observe. For example, we have never observed a doubling of the CO2 in the atmosphere on a global scale and then see what happens to the climate system. This is unknown, right? We are trying to project something into the future and understand what happens, but which has never happened. Has never been observed. We don't have any data about this. So that makes this thing complicated, which is unlike weather forecasting, right? In weather forecasting, you have many of these events that you have observed in the past, and you can verify your model against it. But we are trying to predict in climate change something that has never been observed, and it's just about to happening. Right?
Yeah, wow. Wow, it sounds very complicated for sure. I had another question a little bit earlier from your talk. You spoke about the deep sea temperatures and how they're influenced by the top 50 meters of the ocean that are affected by the sunlight. This is from your simple climate model. Are we measuring the temperatures in the deep sea, and are we noticing a trend there? Since we know that the ocean's moderating the Earth's temperatures, what's going on in the deep sea oceans?
Yeah. So the ocean is kind of organized in a shallow layer, which is about 50 meters, which is a warm surface layer that is interacting on a monthly to many years timescales. Then comes an area in the ocean, which is about a few hundred meters until 700, maybe 1,000 meters, where most of the ocean interacts a little bit on timescales of decades to 100 years. And then comes the deep ocean, which is most of the ocean, that is almost not interacting with most of the Earth's surface. And that changes on timescales of many hundreds and thousands of years. And the very deep ocean is really just interacting with the polar regions around Greenland and Antarctica. These are the main interaction seasons where the very cold winter surface water falls basically to the bottom of the ocean and then eventually comes up somewhere else again. And the deep ocean is not very well observed because it's changing very slowly. If you want to really know what's going on in the deep ocean, you would have to observe it for many hundred years.
Yeah.
So most of the observations focus on the upper 50, upper 700 meters. And then here and then they are observing systems where they have little buoys from the surface of the ocean from the surface to the bottom of the ocean. And they have little spots where they measure these over many decades. But we do observe the deep ocean. quite often indirectly, and some hotspots we observe them directly, but most of this thing of you're observing in the ocean is based on the upper 700 meters. And they actually done with little, what we call Argo floats. So these are little buoys that sink, come back up, send their signal to the satellite, and then they sink down again and they come up again. And they drift around all over the ocean, thousands of them.
Excellent. Yeah, thank you. All right, we've got some chats in the Q&A. Elizabeth is asking, could you please comment on the amount of aerosols and cloud formation?
Not sure exactly what Elizabeth was thinking about aerosols. So there's natural aerosols, and there's natural little particles in the atmosphere that are important for cloud formation. So a cloud would not form if there are no particles in the atmosphere. If the atmosphere would be pure, there wouldn't be any clouds forming really. So clouds form along little particles, and most of them are natural particles. They come from dust, forests, from little particles that are evolved naturally. But then on the Northern Hemisphere, the large industries, they create aerosols as well. And they have, first of all, a cooling effect in those regions. Basically, there are dust particles in the atmosphere, and then they absorb the sunlight, and therefore the surface gets colder. But they can also interact with rainfall and with clouds. But it depends on the kind of particle, on the chemistry, on the size of how they interact with the clouds. And that makes things complicated. For example, one thing that climate scientists notice that most of these climate scientists live on the Northern Hemisphere, and they tune their model to in a way that the aerosols interact with the clouds in a way that actually might not work in the Southern Ocean. So there are complicated things involved in that.
Yeah, right, with the different hemispheres as well.
Yeah, also with the different nature of things. So the pristine Southern Ocean is a very unique atmosphere because it doesn't have all the dust and the dirt in the atmosphere that the Northern Hemisphere has. But most of the climate model development happens on the Northern Hemisphere, and they look at the data that they have from their area, but there's not as much data from the Southern Ocean. And maybe they don't care as much about the Southern Ocean when they are developing the climate models.
Yeah. Okay, we have another question here. This one's from Michael. He says, how can we model natural centennial or millennial variations? For example, Hamlam at the University of Oslo shows clear 1,000-year cycles in the GISP2 Greenland ice core data. Can we parameterize this observational data into climate models?
Yeah, you don't want to parameterize it. I mean, this would be kind of, the climate models do not aim to mimic observations. They try to mimic the underlying physical processes. And from our understanding and observations, we combine this to figure out how this works. So climate models typically run for the last 2,000 years on a regular basis, and taking the changes in sunlight and volcanic eruptions that are known in the past and trying to simulate what happens in the past few thousand years. And from this, we gain understanding of what natural variability looks like. Yeah, we gain this from observations and from models. And from this, we get a fair, good understanding of what the rough orders of magnitudes of variability is. For example, the largest known variability on longer timescales are these natural ice age cycles. And they make the Earth forming large ice sheets over the Northern Hemisphere, and the global mean temperatures changing by about 3 to 5 or to 6 degrees. And this is basically the main reference, and they change on timescales of 100,000 years. And then the shorter timescales variability is typically on a much smaller scale from observations, which is in the order of tenths of a degrees over a decade or so.
Thank you. Sarah asks, what are the main challenges of the global Apollo scale modeling effort that you mentioned?
Money. You have to convince the people to spend as much money. If you think about how expensive it was to get a man on the moon, if you would spend the same amount of money to get a decent climate model, you would have much better climate models. Right? I mean, we're talking about $1,000 billion kind of project, right? And currently climate model projects are all small projects. Right? So if you think about the amount of money that Australia puts into the climate model, it's ridiculous compared to what people have spent to put someone on the moon. So if you would put this amount of intensity, the amount of manpower and money into a climate model, people have the idea that this could actually make the model really work. But
so what about the people? Right now. Yeah, what about the people? Is it, do you think that many climate scientists like yourself are really keen to see something like this go forward?
Yeah, absolutely. I mean, there's a question. I mean, so I've been working on climate models for about 25 years now. And when I started, people said, oh, if you get higher resolution and faster computers, things will get better. And 25 years later, it didn't get better. What it did happen is they start to simulate more and more things, and everything that you put in, like the biosphere, the chemistry, makes things actually simulate these things, but they also introduce errors into the system, and these errors interact. So instead of things getting better, they get more complicated, but they also introduce more errors into it. So definitely we would want this, but it actually just increasing the resolution hasn't happened and hasn't really improved things. An alternative to just increase the resolution and make things getting a bigger computer is to think about alternative ideas, right? What haven't we done in the past, right? Can we make things, maybe develop models in a different way? And one idea, for example, is this artificial intelligence using optimization schemes. But again, this would also use computing power, but it would use computing power in a different way, not just increasing the size of the grid, so many grid data points, but actually running the model again and again and again until you figured out what actually are the processes that we need to simulate and in what way we have to do it.
Yeah, thank you. We've got time for maybe one or two more. Daniel asks, can you integrate high aerosol loading events into the model? For example, Australia has regular bushfires that put large amounts of smoke and other aerosols in the atmosphere that directly affect the local radiation budget. If so, how is this done? And thank you for the talk.
Yes, you can do this. Right? This is what I've shown you at the beginning when in the one simulation with the CO2 simulation, where they put in CO2 fluxes from the surface. In a similar way, you can put in aerosol fluxes. Actually, in the CO2 simulation, it did have the bushfires in it. It wasn't as visible, but it was this white and gray that you saw in the southern hemisphere. And they actually do simulate this. So you can say, I have a bushfire here. I put a certain amount of particles every time into these grid points, and then I see what happens. And you can actually see that the bushfires actually make their own weather, right? So they're actually changing the weather by creating clouds. But when you burn a forest, you are not just creating particles, but you're actually creating water. Because when you burn a tree, the most thing that you're actually creating is water in the atmosphere, because the tree is mostly water. Right? So these things can be simulated, and they have been simulated.
Wow, yeah. John asks, how do your models differentiate between natural and anthropogenic climate change?
Yeah, so in a climate system, there's basically two kinds of variability. Externally forced, that means something in the boundary conditions is changing. And we consider usually CO2 being a boundary condition. Not in all models. So sophisticated models try to simulate the interactions of CO2, so what we call a carbon cycle. But typically CO2 is a boundary condition. So you can say the anthropogenic boundary condition of CO2 is changing over time. And then you see how your model would respond to that. But then most of the climate variability or climate change on longer time scales is internal. So the climate system, especially the atmosphere and also the ocean, is a chaotic system. That means any kind of perturbations, or this picture of this butterfly in New York spreading its wings and changing the weather in Australia, is true in climate models, right? So you take anything, single grid point, change the last digit of the temperature in any layer of the atmosphere, 2 weeks later, every point on the Earth will look different. That's the way the climate models work. So they simulate this internal chaotic behavior. It comes mostly from these convection cells of thunderstorm clouds and so on. And this is simulated in the models. And if you look at something like Melbourne or Victoria or Australia on a shorter time scales of days, months, years, and decades, this is what most of this variability looks like, is naturality. And then on top of this comes then that the external boundary conditions are changing, and that the CO2 leads to a slow buildup of heat, is particularly in the ocean, and that would then lead to a warmer climate.
Excellent, thank you. So I can see that we've reached our midday time limit here, and I can see some people are heading off. So I'd like everybody in the audience to join me in thanking Dietmar again for a really fascinating talk about climate change and the climate models that you've been developing. So thanks very much, everybody, and thanks for coming along.
Yeah, and thanks for inviting me. See you.